Y capaz que como recuperaron esto.
¿No tú de eso?
Ah, bueno, tengo que poner en.
Pues yo tengo un pointer ahí, pero sabes cuando tengo que estar viendo el computador, que sabes que me parecía.
No voy a
No,
poner.
no.
Pointer sí. Pero,
Ok.
bueno, si querés usar esto. Ah, sí, ya.
Sí, sí pasó.
Excelente. Pero déjame que quiero ver una cosa primero.
Por favor.
Si tu estudiante cargó la.
Y tú presentes el juego, no puedo.
¿La cargaste? No, pero no es esta. No, 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 no. Wait, wait.
Que quieren español.
Nada. ¿Qué es esto?
No me conocen. No, que yo desde frente.
Entonces, esto es porque se llama QUARK.
¿Qué más viste?
Juan Montoya.
Oye, cuando la charla. ¿Le conté
¿Es esto?
Sí, no, que tengo un par de días más la gente. Me da impresión, no. Ah, bueno, no, pues eso justo le iba a decir cuando me dijo una de los partículas. Sí, 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 no, que justo cuando dice que cuál es la misma raíz de Max. Sí, pero sí, cuando grito Max, güey, si no tiene. Empezamos. Usted es lo que manda. Él me dice, yo obedezco.
Okay. Okay, we're going to start this introduction. Good afternoon today, and I'm very glad that you was there. Very nice colleague and a good friend. He will talk about the topics such as the status of the CMS experiment.
Okay, so in my talk, mainly for the studies, for them to understand how the things experiment works and how actually we do this research. Apart from that, I will present the status of the external researchers at CMS. Some of them, because as you will see, it's really a plethora of analysis. So, with the so you may have heard, we have the Large Hadron Collider at Geneva. We have a nice picture here of what it might look from the sky. What you see in yellow line here is like a drawing of the electricity tunnel where it goes underground, 100 meters underground, and therefore we are going to focus on this experiment. However, to describe a little bit what the electricity is, we have here all the complex system for acceleration of protons at the Large Hadron Collider, starting with the LINAC here, then passing through all these systems, going up to the LHC, and as you can see here, we have the ATLAS experiment that is our brother experiment, and the SIMMETRY experiment in 1.5. This is a nice picture of the tunnel. Some of us have had pleasure to be there for some time, but this is going to be off now for a couple of years, preparing for the next one. Okay, so a little bit more detail here on the acceleration complex. As you can see, we have not only the light in the LINAC for proton, but we also have this LINAC for ions. So we can collide both protons on and left ions. And of course, I have described already most of the things here, but I want to make it here also a little bit more clear. The other two experiments that are in the energy are Alice and energy. This one focused on big physics, this one focused on heavy ions, and then our two experiments here in Alaska focused on general purpose experiments. So the LHC is actually two tubes that are containing these beginnings of product. You can see that one tube is taking the protons and circulating them in one direction and then the other one in the opposite direction. We make them collide in 4 points where the 4 experiments are, and this collision is actually a collision of clouds that we call bunches of protons. And when we actually make the crossing of the 2 bunches, we expect that from these crossing of bunches, at least one of the protons will collide with another proton from the other bunch. So here you can see a little bit more of the details on the LHC magnets that are the very big ones, blue ones, that are for curving the trajectory of the protons in the LHC. You see here the 2 tubes that contain the beams of protons. And finally, for the collision, we will see something like this, that for the persons that were for the students that were in the master class on Tuesday, they are already used to see this type of display of the events. This, of course, for SYMMETRY. Okay, so now from this very brief introduction of the LHC, let's talk about the Siemens experiment. This is a nice picture of the Siemens experiment, a real one. When the experiment is open, this experiment is made of slices of detectors, so we can take them and move them away one from another to actually make all the maintenance and install other detectors as the ones Alexis were describing before. And what I'm going to do now is to describe all the systems that you can see here in this picture. So first of all, take a look at the overall image of the experiment. You see here the size of the experiment compared to a person here. You can see here the 2 tubes from the LHC arriving at the collision point in the center, the Siemens experiment. And then let me just quote some of the let's say important things about the CNS experiment, and is that the total weight is 14,000 tons. Then we have 15 meters in diameter and something like 30 meters in length. And finally, this very important part of our experiment is the solenoid that produces a 3.8 Tesla magnetic field. So let's take a look in detail of the experiment. Start with the tracker that is actually the inner mobile part of the detector. So going, if I go back, this part that is like a green part in the very center of the detector. It's made of this type of silicon detector. So this is like a cam. So we have the pixel system here made of different layers of this system that will identify charged particles dropping by, and with this identification we can make reconstruct the tracks, the paths of the particles that are made up in the collisions. So here you have an schematic view of all the layers that we have in the what we call the pixel and tracker system. So as you can see, there are many layers that allow us with all the hits from the particles in each layer to reconstruct the particles, where they go, in the vector, right? So one important thing that I want to mention here is that this is an old picture, actually, because after 2017, this system, the Pixel one, that is the innermost one, has been upgraded. So before it was going up to 2.4, so in this sample up to 2.5, something like that, and now this pixel is going up to 3. An important one because now we can make many more things in this increased region for the pixel. Okay. Then let's go and talk with about the ECOL, the electromagnetic calorimeter. You can see that I have here put a circle on top of this yellow bar that are a set of amazing crystals. Let me go back here. So yeah, so these are the crystals mainly that are made up the magnetic calorimeter. As you can see, they are transparent actually. They are like ordinary glass, but made of lead and tungsten. So these are very heavy, very dense material that they take any incoming electron or photon and convert them in basically light. So from here you see the whole cascade of electrons, photons, and positrons that are produced from an incoming electron or photon. And from there, we put at the other end of the crystal a photon multiplier that will detect the light and will tell us about the energy that has been deposited in the crystal by the electron or the photon. So this one is used to detect and measure the energy of electrons and going now to the calorimeter, the next system that is depicted here now in this yellow circle. We have the calorimeter that is there designed to measure the energy of hadrons produced in the collision. You can see that this is made actually of many different subsystems. We have voltage coverage here, and apart from that, a forward calorimeter, a forward and running calorimeter that is a little bit far away from the center of the collision point, actually to detect very forward particles that are produced in the collision. Finally, not finally, but let's talk a little bit about the solenoid. This is very important for us. Our name is compact non-fuel solenoid, so solenoid is in our name. Then the name it also has the word compact because actually all the calorimetry and the tracking system is inside the solenoid, so it's very compact inside this tank. You can see here a view, an artist view of the solenoid. This is a coil of a superconducting material that is put at 2.7 Kelvin to make them superconducting. And then we put something like 14,000 amperes of current to produce the 3.8 Tesla magnetic field here. So actually, we can fit inside the solenoid. It's a very big solenoid. And as I now used to tell, this is kind of the third most strong magnet in Earth. We have two more stronger magnets in Earth. The one from the LFG that is 8 Tesla, and one from China that was how to say, it was like put to work a month ago and for to Tesla. Well, very powerful. If you take a look at the picture, you are seeing the magnetic field that is produced by the magnet, by the solenoid. So, as you expect from a solenoid, you can see the constant magnetic field here inside the solenoid, and then you can see also the outgoing magnetic field line outside the solenoid. One important thing is that we have outside the solvent. So iron dose that we call here and here to actually conduct the magnetic field and try to make it not in this way, not like just a coin, but to make it like concentrated in the iron dose. Now, finally, with the last system, we have the muon chambers that are outside the solenoid, in red circle. This is already related. What with the slides that have been shown by Alexis in the last talk, you see here all the different types of muon chambers that are installed in CMS and working right now, and some future chambers. So the G21 that has not been installed yet, and the M0 that was discussed by Alexis. So actually to bound again on the question from Diego before, you see here that the M0 is after the ECAL and the HCAL. So all these systems will absorb the majority of particles. So here you will have mainly muons. But for example, here, one of the main important backgrounds is neutrons, actually, because neutrons are going all the way. So neutrons can cause also some background noise here in the detector. Okay, so we have three different systems, and the idea is that we will have four different systems, four different technologies. The main one is the RTCs that are installed in the whole area of the muon chambers. They are mainly used only for triggering. Then we have the DTs and CSCs, are another systems mainly used for rotating the passing of the muons, so for geometrical reconstruction. And then we have the GEMS, and we will have at some point some glass RTCs installed over here. Now we know how we detect the particle, right? Now we will have to face with the important problem that makes of detecting them, actually. For that, we know that the LHC will deliver more collision than what we actually can record. It's really a huge amount of data. So for this, we have a triggering system that will select the collisions and will record only a part of it. So we have what we call a two-level trigger system. The first level is called the level 1 trigger, and then the second level is called the high level trigger. The level 1 trigger is based on data cards, right? So in electronic here, so this will give a signal to the experiment in order to record the event. But it will give it to the active trigger where some software will decide if it actually records the event or not. This actually makes a huge difference in terms of what we record from the actual collision from the LHC. So you can see here what we expect in terms of incoming data, the rate. So here, before level 1, is 40 megahertz of data. After high level trigger is only 800 or 8,000 hertz of data. So this is, as you see, many orders of magnitude difference, but this is what we can actually record. With time, we have been perfecting this, and we have another type of strategy with like complementary strategy that I discussed in common to actually save more data than what we can do with the system. But this is the main point of the trigger, to just select the events that are interesting, physics that is interesting, and only record them. Okay. Then, when you decide to finally record an event, you have to reconstruct the information that is in the experiment. So, we use an algorithm that is called particle flow. This particle flow algorithm will relate the information in all these different subsystems to actually reconstruct particles that we can understand. So, for example, here, as Diego was pointing out in the last presentation, you can reconstruct an electron from information from the tracker and from the electromagnetic calorimeter, from the decal. So if you relate these two subsets of information from the detector, you can actually say, I have here an electron. How? Because an electron is a charged particle, so it will make hits in the tracker, and finally it will deposit this energy in the decal. So if you relate these two, you can surely identify an electron in the same as experiment. Then, an important difference here for another particle that is the photon. The photon is not charged. The photon will not leave any heat in the tracker, but it will deposit the energy in the decal. So if you don't have any drugs, but you have deposit of energy in the decal, what you can reconstruct from that is that you have a photon. Then we can make exactly the same exercise, but for charge and neutral hadrons. That if you have a charge hadron, you will have drugs, and then deposit of energy in the H count. And if you have neutral hadron, you will have a deposit of energy in the H count without any heat in the tracker. Then you can see that we have electrons, photons, hadrons, and finally muons is the fifth object that we can identify with the information in the system, in the experiment. Muons are reconstructed mainly from the information in the tracker and also in the muon chambers. Muons are particles that can penetrate easily a lot of matter without needing much information. You can, they will be able to penetrate all the subsystems, even the solenoid, and then go up to the muon chambers. So we take this information over here and this information over here, and we can finally reconstruct what we call here as global news. Okay? So from here, all this information we combine finally into some objects that are called jets. Jets are the objects that combine all the information coming from hadrons, and jets have an important role in everything that I'm going to talk in the following slides, because basically all the different searches that we do at the hadron collider have to deal with this. So here again, a nice event display from CMS where you can see the jets over here, for example. You have all these tracks where you can take and collect with any algorithm for jet reconstruction that you can use. And also here you can see some muons and electrons coming from the interaction. Okay. Then let's talk a little bit about the research program, what we call the physics program in CMS. What you can see here is the CMS Physics Organization. At this moment, I couldn't find the current one. I don't know why. This is not a set of secret names, but anyhow, this is already good enough to discuss what I'm going to discuss. What you can see here is what we call the physics coordinations. These are the two persons in charge of the physics program of the CMS experiment. And from there, you see mainly two things coming out. One are the detectors. So you see here some groups for the different detectors and for the different reconstruction of the object. For example, muons, electrons, atoms, luminosity, and so on. And then on this side, we have what we call the physics group. Okay? And here you see some things very interesting, standard physics, Higgs physics, top physics. But over here you have the three groups in charge of looking for beyond standard one thing. So first of all, supersymmetry. This is the oldest one of all these three groups. Then you have exotica and medium degeneration. I will only talk about findings in exotic. That is where we, as the Antioquia University, we do most of our job. We have done some things in supersymmetry and different generations, but we mainly focus on exotica type of physics. Don't ask me why this division. Nobody knows. Okay? So don't listen. Just a glimpse of how it looks, the Exotica research program. This is what we call a summary of a summary plot of the results from Exotica. Every single line that you see here, that of course me neither, I can't read, but this is not the point of reading this slide. But every single line you see here is one event, the result of. So if I want to come here and discuss this thing, we will have to spend like a week in just one talk. So you can see that we have a lot of efforts towards beyond standard model. I will focus now in three physics research letters that have been prepared and now are accepted by the journals, by the journal. There are summaries of three different efforts in Ethiopia alone, without Susi and without young two generations. Here, there are some small things, little things for supersymmetry, but I won't discuss them. So these three different papers, you can take a look here. Each of them is more than 100 pages, so I will be a little bit more detailed in some of the results, but I will not disclose all the results that are. So one is in dark sectors. The other one is in vector light quarks or leptons. And the third one is in what we call scouting and marking. That I will tell you with more detail. For that sectors, you can read anything from here, right? So, but these are maybe you, but not the ones for yeah. So these are actually the theoretical frameworks considered for the dark matter searches or dark sector searches in CMS. So here you have, for example, what we call simplified dark sectors. And this is the one called extended dark sectors. Extended dark sectors are like the typical ones. The ones that are coming from polygon. Okay? Simplified dark sectors are coming actually from what we call simplified model. One person here is working over there. These are incomplete models from the theoretical point of view that are only made up to actually make prediction calculators for some interesting signatures, but are not intended to be like physical models. Okay? From here, you see that we have a lot of possibilities. I will describe some in detail, and here you see also that we have a lot of possibilities. The only one that I will not discuss at all is the SUSI one, but I will try to discuss a little bit the other ones. The inner doublet model is what? Here, in the extended dark sectors. Yeah. Okay, so let's start with the simplified dark sectors. So here you can see some final graphic diagrams from there. What I'm going to show is a summary, so don't expect like specific diagrams for specific models, because we as CMS, we're more interested in the final states, in the signatures, than in the models behind. So this is more a theoretical motivation than a theoretical talk. And also, you can see here some examples of what the P1 portion looks like. So you have a Z prime, for example, or a dark photon. From P0, you have a scatter here, or a zero scatter, that's making the transition from standard model to a dark sector, dark matter, or a full rigid dark sector. And for the extended dark sector, you have here the most famous one, that is the 2HTM plus A model. And one that is very interesting, that is called hidden values. You see here the complexity of this type of models that I will go to that in a few slides. To go a little bit more on speed one portal, what you see here is this type of diagram that we expect for the reduction of C prime that is coupled to quarks from one side and to dark matter from the other side. This is what we typically call a monojet signature. So you have the Z prime produced with a quark that is radiated from the initial state. So what you will end up is with some missing energy from the dark matter and at least one jet. Let's take a look at these couplings here, because these are going to be very important for the discussion of the results at the end. We usually use this way to call the coupling. So we call GQ the coupling of the mediator to the quarks, and G dark matter the coupling of the mediator to dark matter. And you will see also at some point a GL or a coupling of the Z prime to leptons. This one, in addition, you can see that here actually it's no dark matter produced law, but as the Z prime needs to be coupled, has to be coupled to quarks with this type of search of two jets produced from the Z prime, and also impose restrictions on the Z primes. Then more complex model that like this one, or as a dark button that is coming from a photon from the standard model. This is really related to the talk from Oscar Zapata on Monday, Tuesday, something like that. But yeah, like that one dark photon. For spin zero, what you can see here is the production of a new pseudoscalar that can go into a Higgs, and an additional scalar that is coupling to the dark matter. For the Higgs side, you can search for the Higgs in any of the decay channels of the Higgs. So actually, what we have done is that we have looked for this type of signature in all the channels of the Higgs. So we have looked, for example, the Higgs going to the bar, the Higgs going to ZZ, the Higgs going to whatever you can imagine. Then, if you take a look here, we can also search for dark sectors measuring really well the Higgs couplings. Or if you consider a new coupling of the Higgs, for example, with some pseudoscalars that can go to different channels, this will constrain what we call the invisible Higgs matching ratio that can be one of the portals for producing dark matter at the radiation. And for hidden values, what you can see here is the three main theoretical frameworks that have been studied. This actually is like two, if you can think about it, like two different QCD, like the standard QCD and a dark QCD that is only communicated by a very heavy boson. So you can produce it in the LHC, but you don't see it anywhere else. So this is like a very big window door to communicate this QCD, this dark QCD and the usual QCD. And depending on the dark QCD that you propose, you can have this type of signature, for example, that you produce a couple of dark quarks that will finally produce some jets that are displaced from the collision point. Or you can produce some quarks, some dark quarks, and standard parts, right? So you will produce like ordinary jets and what we call semi-visible jets, because these jets are not completely decaying inside of the tracking system and the electronic calorimetry. Then you can also have some strange, let's say, production, not strange in the sense of strangeness of the charge, but the gluon that via hydronization will produce both standard monoquark, also standard monoquark and dark quarks. Okay. It is really complicated circuit. These are really, really complicated circuits. And this will, really to understand this, you have to go into the details of the experiment. Actually, to do this, many of the algorithms have to be like reinvented or redesigned to really be sensitive to this. So I will skip the details of these ones because they are really special. Important for this, you remember I mentioned that we have triggers, right? Triggers are selections on the object of the collision, on the particles of the collisions, that will make us to make a decision on recording the event or not recording it. Right? This will impact the lower threshold of the events of the objects and will make something really impossible. For example, if we want to use a trigger that triggers in missing energy, so for example, the trigger system looks at the missing energy and decides if it records the event or not, you can see from this plot that to reach the 100% efficiency of the trigger, we have to go to a threshold of 250 or 300 GeV of missing energy. This means that if your new physics is producing 100 GeV missing energy, you will be unable to see it, right? This is extremely important for these dark sector searches because all of them are relying in missing energy. We make some tricks, but this is, of course, one very important constraint for us. Then this one I see also that you cannot read. But what I wanted to see here, what I wanted to show here is the sequence object triggers and dipole triggers. We have also, apart from net triggers, we have electron triggers, muon triggers, tau triggers, gamma triggers, photon triggers, on jets, and so on. In each of them, we will impose some low threshold in order to accept or not accept the event. So, for example, for single object trigger, we have to go up to 115 or 32, depending on what we do, if it's isolated or no. On the electron. So, for example, if you expect from the new physics a electron of, let's say, 8 eV, you won't be able. Then, on the dipole trigger, you have here a table relating electron with electron, electron with muon, electron with tau, electron with gamma, and electron with missing energy. And you can see here the combination. So, for example, for dielectron triggers, you have at least to go up to 25 JV, 25 JV EPT. So, again, if you want to go below that, it's impossible. Okay, so let's start discussing the results. This is the result for the monogen search, the latest one, combining all the run two events, so 2016 to 2018, that corresponds to 137 inverse tomorrow. And what you can see here are the histograms for all the different processes that contribute to these specific analysis. This analysis is actually pretty simple. You ask for events with at least one jet, not only one jet. I know that it's called monojet, but we have seen that if you don't restrict yourself with just one monojet, you will have better constraints. So you ask for events that have at least one jet, and then you plot the missing energy or the missing transverse momentum. This is the histogram for the missing transverse momentum. You see here in the black dots the results for the data, and you see here, for example, for Z plaquette, W plaquette, or other backgrounds in these three different colors. What we expect from the young standard model physics is this type of signal or this type of signal. For example, the light blue signal is an axial mediator with 2 TeV mass with a mass of the dark matter particle of only 1 TeV. And what you can see is that we actually expect, if there is any signal, to have this tail a little bit higher up than what is expected from the standard model. So here, we don't expect any bump particle. There is no resonance possible in the missing energy, but just a slight difference in the tail with regard to what is expected from the standard model. Then there is another very nice search that is called mono-Z. This is, you produce a Z and another particle that decays into a matter particle. So what you actually tag is the Z decaying into a couple of leptons, and then what you measure here is the missing energy or the mass of these events. Okay. Here, for example, you have the missing energy with all the different contributions from the processes in the standard model. The standard starting the course with red gas, then going with WD, VT, and 3 vector bosons. Sorry. And you see that we have a nice agreement, or not nice, depending on of the standard model prediction with the data. Again, for this type of model, you see here in the light green histogram the signal that is proposed here. You also expect like a peak in the tail a little bit higher up than what is expected from the standard model. Then the one that I was describing before, the model analysis, again, it's the same. We have seen the diagram. We produce 1 Higgs and 1 particle that decay into 2 dark matter particles. What I'm showing here is the channel where the Higgs go into 4 leptons, so into ZZ and then 4 leptons. So basically what you do is that you redo the Higgs into 4 leptons search and measure the missing energy. Basically this is the idea of the class. Again, what you can see here is a nice, or not nice, agreement between the data and the standard model prediction. You see here that, of course, the main contribution from backgrounds is then Higgs boson, and again, what you can expect from different signal is the tail to be higher up in counts than what is from the standard model. Sorry. Okay, now let's go to the diagrams where we have the Z prime produced from 2 quarks and then producing 2 quarks. This is what we call the Decays search, because we are actually taking all the events that have 2 quarks and 2 leptons, and then measuring the Decays curve. So here actually you see the Decays one in TeV, not in TeV. We're used to see this plot in TeV, but here we go so high up in energy that we have to put this in TeV. And you see that we are starting at 1.5 or so. And we are going up to 8.5 or so. So this is really high energy that at the beginning of the machine, we weren't sure that we were going to be able to measure this type of diagram. But here you can see. Okay, so actually what is displayed here, you cannot see all the different contributions, because what we do here is not like a Monte Carlo approach, but what we do is actually a method that is trying to fit all the different data points to see if you can be a bump anywhere. Okay, so you are not taking really into Monte Carlo, but you are relying on the statistical possibility of measuring a pump, identifying a value. Okay. So if we take all of these and more results in limits, what you can see here is the current limits coming from all these analyses. Here, for example, we have dielectric, we have dark matter plus jet, so monojet, right? This is, for example, monophoton, one that I didn't discuss, or this in orange is monoclinic. So what you can see from here are all the different limits in terms of the mediator class and the dark matter class, and also compare to a benchmark scenario where we have vector mediator and Dirac Fermi type of dark matter, and also with the coupling of G dark matter equal to 1. So the coupling of the mediator to dark matter. And then GQ, the coupling of the mediator to quark of 0.25. And then without any coupling of the of the mediator to the lepton. If you take these benchmark points, these are the limits that you get from all these different searches. So you see actually that the parameter space is really constrained from the combination of all these searches. Also, if you turn on the coupling to the leptons to be really small, then you can have all these different constraints coming also from other type of searches that are looking, for example, for bumps in the dilepton spectrum. Okay. If you go to the paper, you will see finally that we have all these results getting or tracking the different approaches or the different theoretical frameworks that can be proposed to have a dark sector accompanying the standard problem. So this is really nice set of results that can give us a hint on what is done in terms of this program in CMS. I'm going to go really fast on vector-like searches. So the second paper, discussing that a little more, showing at the beginning. You can have vector-like quarks. So this type of quark that couple both the quarks and leptons produced here from blue, for example. This is what we call the pair production. Or here you can have also vector-like leptons can be produced, for example, as Z, or a heavy neutral particle that can be produced accompanied by a lepton here, for example, or a neutrino. Then, if we go only in the direction of pair production, this paper also has I don't know how many results, but a couple of those results you can see for only pair production all the different channels that have been studied. What you can see here are the names of the vector-like quarks. So this is pair production of a vector-like top. So top and top bar, PB bar, but this vector-like partner. And we have also looked from vector-like quarks with exotic charges. So it is called a daily like a vector-like top because it has the same charge, electric charge at the top, this at the bottom, but this one has 5 letters and this one has 4 letters. And these, when produced, will decay in many different possibilities. So you can have, for example, BW or top E or top C. From all these combinations, you can have all these final states. So you can have 0 leptons, 1 lepton, for example, opposite sign, 2 leptons, same sign, 2 leptons, or 3 leptons, and so on. So you can see that this actually, if you want to be very you want to do all of this, you have to do a lot of work, a lot of searches in order to cover all the possibilities, and I believe that there are more possibilities than this one, but this is a really big lot of work. So just to have a quick glimpse on this type of results. This is an analysis not done by pattern count methods, selection, deep confirmation method, but this is actually a mirror method. This is looking for per production of top quark line top, where the top decays into a P and a W, and then the W decays accordingly. So into jets. Actually, what we do to reconstruct the two jets from the W, but we reconstruct a big jet to contain the two jets, and one jet, small jet for the VC. So here, what you can see is the abronic energy from the big jets that are called AKH. So here you can see again the nice agreement between the standard model and the data that has been collected. This one was also for 2016, so this is only a limited resolution from the one to yeah. So also you can see small signals here, the real if they were there, they would deviate a little bit from what they have. If I put everything together for single production, per production, or for single production, all these type of analysis, you can see how it looks in terms of the limits that we can put for the cross section and as a function of the mass of the top part, the top vector like top, right? Oh, so you can see all the different exclusion limits for all the different signatures, and finally in gray you can see also some lines for the width of the vector like top and the mass of the top being 5% or only 1%. So like a very narrow width and not a very narrow. Okay, so just to finish, then we discuss a little bit on what is scouting and parking. I have described already what is our triggering system for CMS. So the two-level trigger system, the level one, the HRT. Then we have from the coming data, right, outgoing data. We have the usual standard procedure that will keep all the information from data, and this is what we call the standard data stream or prompt offline reconstruction. This means that we take the data and 48 hours afterwards, the reconstruction of the objects will begin. We have the parking data stream that means delayed offline reconstruction. So we take all the information from data, but we only reconstruct it months before. After we have the resource, the computational resources available, we do the reconstruction. But this allows us to not only keep 1 kilohertz of data, but 3 kilohertz of data. Finally, what we call the scouting is like a more aggressive approach to keep more data. That means that you don't keep all the information from data. You do a reconstruction at high-level trigger, and you keep only that reconstruction. So here you have data that is very lightweight in terms of the size of the lens, but you don't have a lot of them. And if you want to compare, for example, scouting with a standard trigger, the acceptance of this, if you rely only on one head, you can see that the trigger system for your level triggering only one head. For the standard trigger, you have to go higher than 600 dB, but with the scouting, you can go down to like 200, 250. So this increases really a lot the acceptance of the experience. We use this actually to put some limits on digest mass searches. So this is the digest mass search, but with the scouting. So this is really a lot of data, a lot of jets, for events that have 2 or 2 clicks. Okay? And this for the high mass regime, starting from 0.6 dB. But here, the most important one that is actually for low masses, because you can go down to trigger thresholds, you can also go down the mass. So here, this is a really novel result for TNS, and really important for the community. Okay, in conclusion, TNS has a really wide and exciting statistical physics program. I haven't even discussed about fusion and beyond generation. We have turned a lot of stuff without any serious hint of new. No hints at all. However, we have pursued a very complete and creative new physics program, and we still have rough to learn and new physics to discover. Just give me one more minute to make a couple of comments more. Very nice picture. I don't see the one. Okay, but I wanted to thank the organizing committee. The local organizing committee has been really great for him. Thank you very much. I have put this scientific buoy in the photo, so if you want to take a look and find the lost buoy, it's there. I just wanted to make a very short content, but we do at the University of Antioch. In terms of experimental physics, is what I do most. If you want to work with us, this is my email. So just write if you feel like that. And thank you very much. Don't forget tonight. I give you the keys for you. Very, very, very any philosophical problem to solve. Thank you very much. They can do questions and stuff.
Yeah. Questions. You can go in this part. Be honest. You should come in.
For which the new physics is now like like trigger or the like they're all in the new physics is in mobility or visual or when
Yeah. That's an idea. We will see it. If the neophysics is beyond the reach of the trigger, so at very low, we think we can. We will do
More questions? What was that? It was too much information to problem immediately. Everyone's.
Pero eso que probablemente están aplicando las métodos de detección de anomalías, como manualmente entrenando todo lo que se parámetros por favor. Esto entra dentro de eso aplicar y si entra tan aplicado en avanzando.
Gracias. Pues eso tiene dos trasfondos. El primero de física y el segundo de estadística. Hay esfuerzos para que se puedan dar estos métodos para que puedan utilizar. Que yo sepa, por lo menos no me he enterado de un análisis público que haya usado única y exclusivamente como lo novedoso. Tal vez lo más cercano, pero es solamente la técnica estadística típica, son estos resultados. En vez de hacer Monte Carlo, lo que hacen es una monte y tratan de ver si no hay una desviación como si fuera un mapa, como si fuera una resonancia. Tal vez lo más cercano. Sé que hay esfuerzos internos, tanto desde el lado de la física como desde el lado de la estadística, por llevar este tipo de métodos a la pero pues yo sepa, no ha llegado a un montón.
de pronto en las bajas slide. Everyone wondering where the let's say important results about current anomalies.
¿Qué tema? No, es la hora con el las anomalías no son tan infrecuentes como uno pensaría. En realidad nosotros tenemos internet anomalías bastante seguidas. La cuestión cuál es que típicamente después de que vemos una anomalía inicialmente a nivel interno, después de hacer todo el proceso de revisión, de hacer todo el proceso, digamos, de refinamiento del análisis, típicamente termina desapareciendo. Las pocas que no desaparecen son las que uno ve por ahí, esos dos signitas por ahí voluntados, o cinco signitas por ahí voluntados. Pero entonces, como decirte que yo puedo apuntar alguno de real importancia, no, por lo menos públicamente. Los vecinos del bloque compadre.
No sé qué tal un poco académica de la pregunta, pero ¿qué opinión tienes acerca de los resultados que se publican? Pues tú crees que si estamos acá en un inicio de periodo por algo tangible o simplemente estamos buscando de dónde venimos?
Muy académico. Es tremendamente académico. De hecho, bordea con filosofía de la ciencia. A ver, cuando pongo yo esta conclusión, es que hemos llevado a cabo un montón de búsquedas muy complejas. Probablemente si no hubieran habido tantas motivaciones teóricas, de pronto hubiéramos volteado tantas piedras, como a buscar, como a escarbar en tantos lugares. Yo creo que una cosa importante de esto es que tal vez tenemos un conjunto tan grande de ideas que nos lleva a tener un entendimiento muy profundo de la física que está sucediendo en el día de hoy. Esa es como mi posición, como mi opinión, porque digamos que siempre está la cuestión de, bueno, no hemos encontrado nada. Entonces, ¿qué es lo que estamos? O estamos haciendo algo mal, o estamos, o tenemos que hacer otra cosa, o no vamos a financiar el próximo colisionador. Y mi posición es que estamos encontrando muchas cosas. O sea, de hecho, el entendimiento de la naturaleza que tenemos en este momento es absolutamente radicalmente distinto del que teníamos antes. De hecho, el hecho de que no encontremos nueva física es un descubrimiento radicalmente importante. Cuando se construyó el LHC, habían serias motivaciones para pensar de que apenas se aprendiera los dos primeros eventos, y hasta el sol de hoy no hemos visto ninguna prueba seria de que está ahí. Entonces, el llamado que nos hace eso es que ustedes, forzosamente, desde el punto de vista de modelamiento, tenemos que cambiar, ¿cierto? Tenemos que cambiar o pensar en alternativas. Y entonces lo que me lleva a esto es que es como que se está acorralando como le estamos como exigiendo a nuestro entendimiento de la física hasta los límites. Entonces, bueno, estamos justamente en el mismo. Nosotros no nos interesa, a nosotros no nos interesa, porque no nos interesa entenderlo bien. Mi posición. Pero el micrófono no va hasta allá.
Luego, en el 2011, se publicó la aromología de Marín, donde y inyectó un W, producido en la que llamamos conciencia. Ya publicar 4.8 sí. Hace que no tengo que ser de ese no publicó nada, no confirmó el chiste. Sería difícil para la comisión para saber que fue creado por algo incluso dijeron de la vez, no conocíamos lo suficiente bien la física de los y que probablemente quizá pudiera responder el cache de esa realidad en este de hoy en día conocemos evidentemente bien la física de los 10 años que son algo de, bueno, que va a tocar excelente, nada de historia de
nosotros epidemias de latas, hemos buscado en humanidad con pelos y señales, pero o sea, la hemos buscado infinitamente y no la hemos podido ver. Es como si quieres, si quieres lo ponemos en términos de las búsquedas de materia oscura. Los que han tratado de producir los resultados de la mano, por ninguna parte. Nosotros también, nosotros que hay muchas veces por equipos y no se ve, y no se ve, y no se ve, y no se ve. Es como la máscara de los grupos. No está muy bien. Acabaron de salir los resultados maestros, ¿cierto? ¿Y qué más hicimos ahí?
Okay, pues thank Jose again. No me parece venir con one. So we move to one talk. We will talk about the systematic study of the structure of P and W.
Gracias. Música. Hi everyone, my name is Thomas Marcela. And we want to talk about the systematic study of the structure of the markets of region. So let's start. So what we know about the matter? We start to talk about matter some years ago, 7 years ago, when we start to talk about the atom. Later, we start to talk about the atoms. Later, we start to talk about the elementary particles. And nowadays, we talk about sub-elementary particles. And now, what we're trying to describe the behavior of sub-elementary particles. But I'm going to start to talk about tools that we use in our research. The first tool is root, and I hope all of you are related with this, because it's an analysis framework used in high energy physics that can give us the possibility to analyze the action of data. The other tools are these three: math graph, analysis. Math graph can give you the possibility of studying the platonic collisions, PTR, the atomization, and Kai process, and then regulates the detector. The main concept of our studying the jets. Jets is the physical object that is in the result of a shower due to an atomization process. So it's very interesting to reconstruct the jets because we get the result particles of the jets, not the entire particles. Nowadays we use two algorithms basically called algorithms that are the iterative calls and the sequential clustering. They use CMS and Atlas as a sequential cluster, and we use in order to start the anti-Cat algorithm that is a kind of sequential clustering algorithm. The algorithm that we use here is 0.4. The useful radius in this kind of starting from 0.4 to 0.7 is 0.4 in this case. And we studied these three processes. The first one is the C process, the C prime process, and the glue process. All of them because in VM and V bar. We call the C process as a high PT process because the barrel mass of the C boson is more than 90, and you to have a lower mass. This case of the supreme is a mass order of around for GeV, and the gluon, for example, doesn't have mass. And the gluon, for example, have a behavior with a big and low BT. For that reason, the first process, the C process, we call high BT, and the other two low BT. So let's continue with the results. So our first contact with the data we analyzed were the jets correct. So as my partner said before, this column is both for the C prime and this one for the UCD process. Here on the left we have the C process. So in other words, we have a high PD, low PD, and low PD. At the how we put is the jets in this product were different, but we wanted to know how are they different, what geometric or energetic properties are different in each of them. So again, we have high PT, low PT, and low PT. This specific plot is a contour level where we took the jet of the process, we set at the radial center of the jet, and we increase the radial value, the radial position. And as we increase it, we measure how much percentage of the momentum of the jet have we reached. So in the x-axis, we have the air column, and in the vertical ladder, the axis, we have the percentage. You can see clearly the different behavior between high PD and low PD. If you're asking what is this second row, this lower, it's basically a zoom just to show in a clear way how is the behavior in this. But at this point, we can see clearly that high PD jets and low PD jets have a different behavior and structure. So this is again is kind of a similar plot. In this case, we are in the jet, we are looking at the particle with the maximum PT, and we measure both the radial position and its PT. Once we have the PT of this particle, we take the ratio, the momentum part, the PT of this particle, and its own jet PT. And we can see different behavior between IPD, low PT, corresponding to C and its prime CD process. And in other words, we can see the x-axis is this ratio of PTs, and the vertical axis is its position. So in the high PT process, we can see this maximum momentum particle tends to have a ratio of 1 with its own jet, and it is used tends to be closer to the center of the cone. In the LSPT, this maximum momentum particle have a lower momentum compared to this own jet, and this particle is set far from the center. As we can see, there is a correspondence with the PT. In this case, we are this value, so I think it's not very clear for vaccines. But the boundaries of the graph cards. So here in the QCD process, we can see the first jet, in this case, the progress of the percentage of PT, and I mean the R position,
In this case, we have a group of the jets of 3 GB, 5 GB, 8 GB, and 20 GB. You can see two things. In the 8 GB code, the second level splits in two keys, and this is given by a lot of statistics, and it's very clear in the 20 GB how this changes. But also, you can see how this behavior change instead of being this small straight line to a curve like this. But this and have that much. This doesn't happen in the normal symbols. In the same codes, 3, 5, 8, and 20. And so the conclusions is we were looking for the difference in low digits and high digits, and we found them. Also, the cipher process and the exclusive process behave more or less the same in every measure we did. And that's it. The difference between these low and high digits, where basically is distribution around the jet and the energy or PT they have. So
So this was the first part of the job. The first part was studying, make a systematic study of what happened with the jets. And now we need to make sure that all right, as we have seen. And now we want to start with the second part that is to use some machine learning tools to make a Italian process of longevity. Because nowadays we have this current process of IPT, so we're training for longevity. And this is the GitHub or where we have all the study. So
Yeah, no, it's all in the what? All in the auditory means the okay that. Coming first place in the second round as anyway. Okay, questions you.
First of all, the próximo de Colombia Network Channels. Or what in Twitter or next. Okay, my question for the pretty differentiation, the just coming from the use of the display purpose is important. This is also important for both PD, have you already checked display purpose, display purpose. So we have not checked that yet.
Other questions? I have a question. Did they come from CMS or that's they?
yes, yes, as mentioned, use Mara, BT, and others
Okay.
because we make a hallucination.
More questions?
In the past of tools, I don't know if you mentioned it already, yes, but I don't understand very if what is the lane of the graph. In some letter, basically, what is the mean of blue color or yellow color?
Well, it's basically where control plots. So we have the 2D histogram and you were right. And the letters, the space yellow color, are more higher
or more counts in the, so this is bigger. So we go with a bigger count, and that's it. Another.
Not we sang. So, Boson.
Espero que sí. No sabría decirte, pero que sí. Sí, yo lo escuché. Así es. Espérate que me moneda así. ¿Sí? So Jorge is going to start with this.
Transmission. Today we will explore how the result of the observed and classified by the images to simulate the power transmission, precision, and emission. And in the power transmission process, ensuring the quality of all lighters, we requires the precise passing.
Maybe you put the, I think you put the, el sonido está saliendo de ahí, ¿no? Maybe you put the, si pones el micrófono ahí. No sé si.
No, yo le propongo
En la salida de ahí, lo vuelvo a pasar.
Ah, sí, acá.
Voy a poner por acá. A ver si puedo. Otra. Porque no me deja. Ah, esto. Sí.
It's the transmission. Split images to simulate power transmission and sensation animation. Keeping power transmission process ensure the quality of the animation is crucial. It requires the precise classification processing of images representing inspired characteristics from the purity to the continuity capacity. Together, it's a massive practical language means neural networks that analyze images to maintain specific patterns. The neural network models trail hundreds of images in to accurately identify the images that meet the necessary standards for our transmission. The process begins with capturing images of the person. These images are processed to enhance critical details. The neural network evaluates each image determining its material or characteristic transmission or its code. It's not to be facilitation. On visual suppressions, minimizing human errors and increased accuracy, optimizing cost and selection of optical findings for power transmission. The implementation of neural networks in optical fiber classification represents a significant advance in power transmission technology. This means the potential electromagnetic fields that have contaminated the electric detection process and should come and a basic infrastructure.
No, me faltan kilos. No, los filmiamos.
Ah, sí, está bien, suena bien. So Jorge is going to talk about the characterization of these fibers, particularly that with using bigger image.
Thanks so much. We're going to talk with Spanish. Buenas tardes, gracias por estar acá. Vamos a hablar de caracterización de los cortes transversales de fibras ópticas
para saber si son aptas para transmisión de potencia. Entonces, esta charla está directamente conectada con la charla del profesor David Martínez, ¿sí? Y lo que se va a aportar aquí es, o sea, quiero resaltar la importancia de la fibra óptica en este proyecto, en el detector de tabla, porque a través de la fibra óptica se va a transmitir poder. La fibra óptica, ya lo dijo el profesor David, va a estar cambiando de temperatura ambiente a temperatura criogénica. Y lo refiero a este artículo que es fundamental. Bueno, entonces la pregunta, ¿cómo ayudar a determinar si un cable de fibra óptica es apto para transmitir potencia? Entonces, la formulabilidad de la fibra óptica corte transversal, estamos centrados en verificar el core y el clad, ¿sí? Porque ya lo demás, las capas de coating, el bobby y el PD, ya le provee integridad. Estamos centrados en el core y en el clad. ¿Cómo clasificar, cómo ayudar en el proceso de clasificar esas fibras ópticas? Entonces, la idea es que se fotografía el borde transversal de la fibra óptica y con base en esa fotografía hay que decidir, se debe decidir si sirvió o no. Entonces, le vamos a pedir ayuda a la inteligencia artificial. Entonces, se ha diseñado los resultados previos, los diseños previos, una red neuronal. La entrada para esa red neuronal es la imagen, ¿sí? La imagen ya viene, se toma la fotografía cruda, pero se debe hacer un preproceso. Luego entra a una capa convolucional de 32 neuronas. De ahí pasa a una capa convolucional de 64 neuronas. A partir de ahí se aplanan los datos que vienen en multidimensión para que ya pase a la capa densa. Se hace una capa densa de 64 neuronas. Y luego se hace una poda de neuronas. Entra a la capa de 32 y luego nuevamente poda y salen. La salida es binaria. ¿Sirve o no sirve? Muy bien. ¿En qué se trabajó este proyecto? Se está trabajando Python, fundamental trabajo en Python, con Colab y con la ayuda de la GPU. También se utilizó la biblioteca, principalmente la biblioteca TensorFlow, para trabajar en la arquitectura de lentes neuronal, el generador de imágenes de datos, ¿para qué? Y el TensorBoard, para trabajar estadísticas de aprendizaje. NumPy para los arreglos y las matrices, CB2 para el procesamiento de imágenes, Matplotlib graficarlas, bueno, el sistema operativo, la biblioteca del sistema para manipular los archivos de las muestras, y el scikit-learn para manipulación de muestras. Bueno, dificultades que se han tenido con este proceso. Quiero que ustedes hagan el ejercicio de verificar, que me cuenten, cuál es la muestra buena en la popular. Ha sido un límite. La dos la 1. Y bueno, aunque uno a primera vista diría la muestra 1, ¿cierto? En la columna izquierda tenemos las muestras crudas, en la columna tenemos las muestras preprocesadas. ¿Va? Entonces, la muestra buena es la 2. ¿Qué más dificultades hemos tenido? Teníamos muy pocas muestras de entrenamiento. En los tutoriales, algoritmos, libros, siempre se habla de más de 20.000 muestras de entrenamiento. En este caso teníamos 29, poquitas. Mucho ruido en las muestras y las fotografías a color. La metodología se sobreajustaba o se subajustaba. O las clasificadas todas buenas o todas malas. Y
pues no existe una guía mágica que le diga a uno, diseñar la red neuronal así que te va a funcionar. Eso hay que empezar a trabajar con estrategias de prueba y error hasta que cuadre. Y se necesita una máquina que trabaje bien, que trabaje rápido. Bueno, muy bien. Estrategias de solución para esto. Entonces, aumentar el número de muestras basados en las existentes, mutarlas para que puedan, pues para que se pueda trabajar con una muestra de entrenamiento. Preprocesar las imágenes. Si no se preprocesan las imágenes, se pierde el tiempo, literalmente. Trabajar con estrategias de regularización, L1 o L2, nos vimos por la L2 y hacer poda de neuronas. Luego trabajar pues, con redes neuronales artificiales y convolucionales. Si se va uno solamente con las artificiales sin convolución, más complicado para capturar patrones. Aprender la generalidad de los defectos y generar nuevas muestras, porque las nuevas muestras las generamos mutando las muestras existentes, pero sería una estrategia nueva, crear nuevas muestras, tomando los patrones de las muestras que ya existen. Y trabajar desde varios frentes de preprocesamiento de imágenes para poder solventar la falta de muestras. Bueno, resultados preliminares, un poquito, pero la neuronal, después de hacer el proceso de entrenamiento, devuelve una precisión de 80 a 90% cuando se prueba con muestras no vistas en el entrenamiento, tiene una precisión del 72 al 79%. Y cuando se vuelve a pasar la red, clasificando las propias muestras de entrenamiento, se va de 80 a 90% de precisión. Bueno, aquí hay unas imágenes clasificadas. No se alcanza a ver en la etiqueta superior. Dice la preexistente y la que devuelve la máquina, la clasificada. Y en este caso, en esta instancia, clasificó bien 3, clasificó mal 1. Bueno, muy bien. Conclusiones. El número de muestras es importantísimo a la hora de entrenar la red. Ojalá sean muchas, entre más mejor. La calidad de las muestras incluye en ese proceso de entrenamiento. Evita preprocesar las muestras, porque si no se procesa puro rollo. Hay que mejorar las heurísticas del diseño de la red neuronal. Debemos contar con una buena máquina para trabajar y Google Colab ayuda muchísimo. Y muchas gracias.
Chata, ventas.
Pagan el cola.
Estamos envueltas para pagar el Colab.
¿Y qué máquinas usamos? Que necesitan una buena máquina.
Principalmente que tenga la tarjeta NVIDIA, la que permite hacer procesamiento con GPU.
¿Y cuánto tiempo tarda?
Pues una comparación. Yo la corrí en mi portátil y se me bloqueó. La corrí en el computador pues, de la oficina, que ya es un poquito más respetable, y se demoró 25 minutos. Y la corrimos en GPU y se demoró 1 minuto. O sea, es demasiada la diferencia. Entonces, se necesita una buena máquina.
¿Más preguntas?
Desde la parte del procesamiento o de la como que ha tenido que para tener pues, no sé, la cámara, pues porque creo que debe ser muy difícil estos algoritmos por ejemplo, la posición, o por alguna variación que pueda tener de la tomanización de los datos.
Bueno, para responder eso, profe, hay un aparato que permite estandarizar la toma de fotografías de la red. Muchas gracias.
Pues muchas gracias por la charla. Quería saber nos podrías contar un poquito de cómo es el proceso de ocupar las imágenes que ya tenías y pues cómo influyó eso la cultura del proceso de validación
De todo lo que es hecho. Gracias por la pregunta. A ver, por acá yo había colocado, digamos, la imagen cruda no es totalmente cuadrada, ¿sí? La imagen cruda rectangular, pues, las pongo. Y lo que se hizo fue con unas bibliotecas con unas funcionalidades de CV2, la biblioteca de Python. Con esa biblioteca se centró el círculo y entonces se recortó la imagen, entonces por eso quedó de fondo negro. En la etapa 1 es la imagen ya recortada a cuadro, en la etapa 2 es la imagen en escala de grises. Es muy imperceptible el cambio, pero ocurre. En la parte 3 se corre un algoritmo que se llama CAN de CV2 que busca los contrastes y entonces los delinea. Y en la figura 4 es la misma 3, pero con los delineados más gruesos. Entonces ahí se asegura pues, que sea la misma muestra, ¿cierto? No se le hace una transformación pues, más agresiva. Y para montar las imágenes, para poder generar nuevas, se utilizó la herramienta del Image Generator, que lo que hace es rotar la imagen, la pusimos a rotar aleatoriamente entre 0 y 90 grados, y luego que le hiciera flip horizontal o vertical. Entonces así se generaron, bueno, básicamente de 29 muestras, utilizamos 21, el 75% aproximadamente, para generar muestras de entrenamiento y validación, y las otras 8 de testeo. Pero las muestras de entrenamiento se multiplicaban por 20 y las de testeo por 10. ¿Sí? O sea, quedaba como 420 imágenes de entrenamiento y 80 para testeo. Pero si le ponía aún más, se colgaba la máquina. Por eso necesitaba una buena máquina. Pero te respondí la pregunta, te queda claro. Para.
Gracias. Más preguntas. ¿Cómo? No sé cómo me surgió ahora, pero sí de lo que ¿cómo hace uno para asignar un error a este tipo de procesos de utilizar redes neuronales y asignar el error al término?
Muy interesante la pregunta.
Sí, era de ese eso bueno, eso es lo que generalmente la nueva manera de hacer el dato como que los tiempos más sencillos por su índice de error y se va a un proceso más.
Ajá.
Ya pues se va a ver un poco funcionalidad de cambio de datos y no se puede actuar de estilos y modelos y empresas pero hay muchos tipos de proyectos. A ver, una interés. La gente, los éxitos prioritarios son cosas muy identificadas. Pero al final, a veces las imaginarias de ella es misma.
Permíteme, a ver, yo digo mi mano.
Lo que se ve es el machine learning, pero hay varios modelos que se pueden asignar.
Sí, sí, sí.
Hay que hablar de algo que puede ser un humano, hay una detección de las bajas.
También les complemento un poquito. Acá tengo otra. A la izquierda vemos un conjunto de datos linealmente separados. Ese es el ejemplo más sencillo para construir, digamos, una red neuronal, un ejemplo sencillo, es el perceptron original. Yo tengo las muestras de tipo 0 arriba, las muestras de tipo 1 abajo de esa línea o hiperplano separador. Las etiquetas de arriba son 0 y las de abajo son 1. Yo pongo a un plano aleatorio inicial. Puede que sea atravesado, que no las clasifique bien. Entonces yo le digo a la función clasificadora que me diga esta muestra de qué tipo es. Entonces, si él la hace mal, yo ya sé cuál es la buena, entonces ahí empiezo a sumarle al error. ¿Listo? ¿Qué hay a la derecha? A la derecha hay una construcción del espacio de búsqueda. Y esa función, pues eso es infinito. ¿Por qué? Porque cada mínimo local de la función es una respuesta, es una solución que separa las muestras. Y en esa separabilidad lineal hay infinitas reglas que pueden dividir ese conjunto. Entonces, el caso más sencillo es ese. Pero si yo ya tengo una imagen, estas imágenes salieron de 820 por 820 píxeles. Esta de aquí solamente tiene dos valores, X y Y. Pero una imagen de 820 por 820 da 650.000 de características, 650.000 de dimensiones. Entonces, artísticamente, yo le diría a la inteligencia artificial, dijo que una montaña bien clara. Esta sería el espacio de búsqueda para utilizar una función que tenga demasiadas. Y ya es como se construye la función.
Gracias, Jorge. No veo, entonces te agradezco.
So we continue with Jose Antonio. He will talk about tau polarization in to the tau pickets.
Everyone, so today I'm going to talk about polarization is similar to the tau case. So the main idea we need studies is to use the conclusion the tau polarization and try to use the results in a bigger general phenomenological project research with visited John standard model. So let me start with a brief summary of the talk. So I will start with the physical motivation, where the main idea is try to connect the tau polarization studies with the general picture of the phenomenological project, some theoretical aspects where the main idea is try to observe what is the correlation between the differential cross section with the polarization, specifically of the tau. Some experimental observables, such as CMS experiment, ATLAS experiment, and summary of the partial results will be obtained at the moment, and finally some reference to the stats. So let me start with the general picture of the project. So the main idea is to develop a technique and computational tool to infer the polarization of a specific particle, but only with information of the children particles. So what is the idea with this? We have this specific technique and tool. We can define a polarization observables to obtain for one specific condition experiment with two taus, try to observe if the mod particle, for example, is a secret boson, is a Higgs, is a QUARK, etc. Given that the particles are differentiated between differentiated given the structure of the spin, no? The scalar particles and the vector particles. So the main idea was shown today in the morning section. We have a main particle, the model particle, and we have the children particle, the case. The main idea with this type of the case is that the information of the model particle are stored in the children's. So, for example, we can use the information of the children's to reconstruct the total charge, the momentum, the total energy, etc. But the question that started this analysis was what happened with the speed. We know that speed is related with the momentum angular, and we know that the momentum have to be conserved in process like this. So the reason, the main question was, okay, we know that there is a relation between the final stage with the initial stage related to the speed. So only to remember that the speed is a variable that if we want to measure that variable, we need to define a specific axis, normally the z-axis, and the speed is the projection of the variable speed in the axis. In the the conventional example is the electron, where we have two possible orientations, the minus orientation and the plus orientation. If we consider the scenario, we have that the particle is moving into a specific direction, we can use the helicity. The helicity is the projection of the speed, but specifically in the momentum direction. So, and depending on the direction of the speed and the momentum, we have a positive value of the helicity or a negative value.
But what happened? Given that the helicity are defined using the momentum variable, and the momentum variable is a variable that depends on the reference frame, we can have one scenario. For example, in one reference frame, we have the helicity is a positive number, but we can use reference transformation, and find a new reference frame where the momentum is the negative of the initial momentum. So the helicity will change the signal. So we have a negative value. For that reason, the helicity is not an ideal variable because it's not invariant under transformation in the reference frame. But there is a more powerful variable, this is the chirality. So let me start with a general picture of the chirality. The main idea is we have a real object, we have a mirror, and we have the reflection of the real object. And system is chiral if the real object is equal to the reflection image. And a chiral system is when we have a real object and is the same the reflection image. So that because the standard model shows that there is a difference, it's a chiral system because the electron receptor we have the S into left interaction, and this depends on the particle is left or is right. And what would be the chirality? So if we consider a specific scenario, but two scenarios, the mass particles are the characteristic case, we have that a chirality is the same of helicity. In our case, given that we are the plan of the future is trying to use information with a similar condition in the CMS experiment, which we have in the ultraviolet is the case. So through the next slide, the information right on left will be very similar to say helicity positive or helicity negative are equivalent to variables. So okay, so retreating the T decay to the 2000. So given that we know that some specific variables and quantity properties have to be conserved, we can define a restriction in the finite state composed. So for example, we know that the total charge will be 0 because the C is a neutral boson. So that implies that the tau and the other tau will be particle and antiparticle. And if we consider the different scenarios where we have that C only can decay in specific two ways. Where we can that the tau is a right hand side and the tau is a left and right hand side. With respect to the anti-tau, we have that given that is the antiparticle, if the tau is right, the anti-tau will be left. And what happened with the C polarization? So the C is a boson, which is equal to 1. So the different projection in the C axis will be -1, 0, and 1. And as I mentioned, so depending on the projection, we have different possibilities. So when the projection is different to 0, we have transverse polarization. And specifically, when the projection is equal to 0, we have longitudinal polarization. So if we consider the case of the C, given that there is two possibilities in the tau case, the left and the right, we can define a theta angle, you can see here, and we can estimate the differential cross section in all the possible variables of this theta angle. So, okay, but how is the procedure to calculate that differential cross section? So the idea is to use the standard model because this control region is only the test control region to understand the details related to the polarization. And we use knowledge about the C boson. We know that is with interaction and only to right hand side particles and left hand side particles. But it's important to highlight that the coupling is different if the particle is left or right. So this results imply that the results when we consider C decays to taus, there is not the same results when we consider left or right. There is an asymmetry between the results. And also, given that we are considering the CMS condition, because we put that the C is created by QUARK process. As you can see, it's summarized the Riemann diagram on the right hand side. But what happened? If we impose the initial condition, the quadrant and the quark, and the final condition, the tau and the tau, we will have a problem because there is more of one favorite diagram that contributes to the differential cross section. The most in the first step, the most basic are the two diagrams which you can see here. When we have the contribution is one part of the C boson and the other part of the photon. So the differential cross section will become a combination of the results. We will have the contribution of the photon, the contribution of the C, and one difference term. That is the combination of the two decays. The good news is that given the standard model, we have a strategy to solve that problem. Is the using the scattering amplitude, and the relation between the differential cross section and the scattering amplitude is the square. So if we calculate the square normally, it appears the interference term, but only I want to highlight that we need only calculate separately the gamma effects and the C effects. When we calculate that in terms separate, when we calculate normalization, we will have the interference term automatically. So, okay, how can I calculate that terms? So, let's start with the figure rules. So, is the normal rules that we use to study processing the standard model. So, you can see here two different columns. On the left hand side, the photons, on the right hand side, the C boson. And the main difference between both the scenarios is only the propagator and the vertex factor. So only to highlight that the vertex factor contains the vectorial coupling in the C boson and the axial coupling in the C boson. And remember that the coupling depends on the chirality of the particle, left or right. So we have the different Feynman rules. So we can use the level strategy, where only we put the different information in the correct way. For example, you can see here the amplitude scattering that was calculated, where the left-hand side corresponds to the information on the left-hand side of the diagram, that is the QUARK part. The final part of the amplitude scattering is the tau anti-tau, or in other words, the permanent anti-Fermi, and in the middle we have the propagator. Initially, we only consider the propagator of the C, because we can see in the previous slide that there is an equivalence between the C and the photon. So if we do all the calculations, try to see what is the probabilities of the Dirac fermions, we find the question that you can see on the bottom of the slide, where you can see that in general there are different terms in different colors, like blue, violet, red, and green, and these different expression terms correspond to different combination of the right and left hand side. So let me start with one example. So for example, one term of previous slide is this, and you can see that we can understand this term as the interaction of the right quark and the final space or by right tau. What happens with this? If you know, as I mentioned previously, if we impose the condition of the particle, the antiparticle conditions are established because our particle is particle. So for that reason, in the following slides, I only mentioned two letters. The first corresponds to the information of the quark, and the second letter corresponds to information of the letter. In that case, the nano. So, and also, I would like to highlight that if we develop the different steps to the calculation, we observe that in general, the scattering amplitude depends directly on the coupling constant, the GR and GR. And you can see that the superindex is different because we have the information of the fermion and the quark. So if we can extend the result, but not decay, right, some decays left, right, left, or left, we only have to put every equation but changing the information of the component. So as I'm sorry. So we know that, okay, we calculated the scattering amplitude, we know what is the mean of each part of the scattering amplitude, and if you remember, there are 4 terms in the scattering amplitude. So, as I mentioned, the different terms are related to the different combination. On the bottom, on the left-hand side, corresponds to the initial condition, right. The next is the left-right, the next is the right-left, and the final is the left-left. So we can use the methodology, which is the information of the constant contact, and we can create the table that you can see here. So the table summarizes the different combinations. You can see that there is different products, right, left, left. And given the equivalence between the photons and the C boson, only you can see here the different equivalence, we can complete the other part of the equation using the bottom case. And for example, if we want to calculate the we got to calculate the process, we have, for example, a right quark and the final state is composed by right tau, we can calculate the square of the amplitude matrix, and we can see that is very easy because we have all the factors here. But okay, the problem with this is that okay, the main objective is try to find the differential section in any specific case of the C prime K. So we mentioned that there is a correlation between the differential perception and the scattering amplitude, and the relation is mediated by the central mass energy X bar. But what happened? In the real experiment, we can impose the initial condition of the decay, that case information, for example, in C. For that reason, we have an average of different polarization. You to remember, I mentioned 3, 4 slides, that in the case of the C, there are 3 different polarization modes, 2 transversal, 1 longitudinal. So for that reason, you can see the expressions are divided by 3. And again, given the same structure, when we move to right, left, etc., we can start with the initial condition, for example, the right, and see what happens in the differential procession. So you can see here, with this is trying to do the equation. Remember that the tree is given the different polarization in the C Boson, and only using the information of the data table presented in previous slides, see the expression here. So I would like to connect a differential cross-section depends on different variables. For example, the energy in the central mass, the charge between the two, between the fermion and the quark, and the constant complex that you can see here. And again, given that it only depends on the specific constant complex related to the polarization state defined, if we want to extend the results to the left, right, etc., only we have to modify the specific condition. So you can see that is essentially very easy to move to the first to the next expressions. But okay, the problem is okay, the result presented in the previous slide refers to a specific case of the quark, but it's very similar to the previous discussion. I didn't put the specific condition of the quark in the experiment. So if I want to measure the polarization, I have to calculate an average. In that case, we define, for example, the differential cross-section, where X is the combination when we consider the tau is right and left, and right represents the state specific for the tau. So if we calculated that and develop all the calculations, we observe that the difference we consider right or left tau is only one sign, and the sign is defined by the variable lambda here. That's why when the tau is right and minus 1 when the tau is minus 1. So the first question, what is the correlation between the differential cross-section and the polarization is here in this equation, okay, the lambda factor. But okay, so we have the correlation. But we can move the analysis and try to define specifically the polarization. So given the asymmetry between the left and the right particles, we can define the polarization as the difference between the number of right side, the right hand taus minus the left taus. And given the correlation between the number of events and the differential cross-section, we can use the result presented in the previous slide. And we can obtain the expression of the tau polarization. And given that the tau and anti-tau in the final states with the Decays are particle and antiparticle, if we want to obtain the result, but in the case of the tau instead of the tau, in the case of the anti-tau instead of the tau, we only have to include a minus in the result. So if we develop the calculation and calculate the angles between the different possible theta angles, we observe that polarization depends only of the different constant couplings defined in the weight sector, GB and GR, the vector part with GR. And what happened with this? Okay, we have an expression that related the tau polarization, but the main idea with this is try to connect the decay products to the model particle. And remember, the model particle in our case is the tau. So only to remember that we have the tau is an unstable particle, the lifetime is around 300 femtoseconds, and the tau decays in different ways. The weights can be divided into different columns, the leptonic decay and the elliptic decay, and specifically in the elliptic decay, we can define two bigger blocks, the one block and the 3 blocks, when the number only represents the number of charged ions. So we concentrate the studies in the one-prong case, when we have only one ions in the final state, and using for momentum, I don't want the details here, but it's very quotation codes easy. We can calculate that the cosine theta is this variable is the angle between the tau in the tau raised frame. So this implies that the tau velocity is equal to 0. And we obtain that in the first approximation of this variable is equal to 2x minus 1. What happened with this? We can use the variable x, that is the ratio between the sharp pion with respect to the tau, and we can use that variable to estimate the polarization. Remember, using information of the final state. For example, here, these are results presented by Adams and CMS, where you can see that there is two different plots, but two different curves in each plot, and shows that depending on the specific condition of the tau, we will see any difference. For example, the blue corresponds to the lambda equal to -1. Remember this. The tau is a left particle, and the violet is the right tau particle. So the observable for the status will be x. And also, we found that there is information of another important variable that is the symmetry between the particles in the fact that take the energy of the pion minus the energy of the neutral particles, and again, there is a difference that we consider the polarization left of the right of the tau. So finally, this is the status of the project. So the methodology was try to replicate the results. The idea was to try to use the three different tools that you can see here, starting with Marín to simulate the process to particulate level, continue with Vidya to simulate the solution shower, and Delphis to simulate the technical conditions. So when we compare the results of Marín, the particulate level, our results with respect to the reference result, we observe how the between the results, but at the moment we have some problems with Delphis because we implemented some constriction in the tau implication, but at the moment we have not replicated the result that is in the previous slide. So in summary, so we did all the theoretical calculation in the tau polarization, we observed the incorporation between the differential procession and polarization, we consider the difference between the vertical photon and Boson, the different scenarios and the average between them. And we obtain or we see some possible observables that we have to test. For example, the X variable that I mentioned and the symmetry variable that I mentioned. So this is the reference. Thank you so much.
I hear you was a little bit close to the motivation. Sorry, if I am equal, this kind of measure is a very measure in both plasmas and CMS. Is that right?
Yes, exactly. CMS
Is compare. So what is?
Okay. What is the idea? The idea is initially try to understand what is. I'm sorry. What is the idea? The idea is try to understand what is the effect of the polarization of the panel state and which observable is useful to observe that variable difference between the power in CMS condition problems. So initially, because the initial part of the project, we consider a control region and non-control region. The C indicated two tasks. Because we know that given the topology of the C and the condition given by the standard model, we know that, for example, only there are two possibilities of the task, right? Or the number. Okay. What is the idea at the moment? The idea is, okay, we try to study this, we try to replicate the results presented by CMS and others, but using our methodologies, MAD, PTIA, and DEFES. When we observe the same results of the CMS and the reported, we can use the same methodology, software, etc., to extrapolate to searches of new physics. For example, this is prime, Higgs, because we can differentiate the new particles using the spin of vectorial or scalar, etc. But yes, this is the first step. Only try to understand and see if we can replicate the results. Is perfect.
More questions?
No, the same.
Maybe to replicate the result, it is necessary to consider one correction or not. Because all the calculation was at 3 level.
Yeah, yes, exactly. Yes. But okay, so for example, when we okay, I didn't mention the details of the CMS and Atlas studies, but for example, all the calculation started using information by Atlas and CMS. So we try to replicate all the calculation, the middle of the steps, try to see what happened this, why is the equation, and for that reason, we expect that we will see the same final states pop beyond. So we expected initially that we will replicate the result, but at the moment we can predict the results here. You can see here. For example, you can see that. For example, this is the preliminary results to the first detector element, and you can see that there is no difference between here the tau and the anti-tau. And suppose that the CD case in tau and tau, so one particle will be right and the other particle will be left. You can see that there is no difference. So we are going with that. Okay.
Yeah, the problem is in that.
Maybe because
Well, that in that part of the study. Okay, we think presentado. And we move to the last talk. Christian. So Christian will talk about the effects of interference in DSM production and detection of tau at the NHC.
so we should study Spanish. Esto es un proyecto que hemos venido realizando en la Universidad de los Andes, en conjunto con la Universidad Católica del Perú. Entonces quisiera comentar cómo se marca, por ejemplo, el trabajo de Boson y esto en este proyecto. Entonces, quiero hacer una pequeña introducción, una motivación, explicar un poco más de fenómenos acerca de interferencia, mostrar un modelo que ya hemos estudiado, mirar los resultados y dar algunos ejemplos. Entonces, como siempre, partimos del modelo estándar. Quiero comentar que en el modelo estándar, el sector leptónico se trata de manera de una de las interacciones electrodébiles y esa propiedad se conoce como universalidad leptónica. O sea, la universalidad leptónica. Tenemos algunos indicios, por ejemplo, las anomalías de energy star de las mediciones versus la predicción del modelo estándar nos dice que puede estarse violando la universalidad leptónica. Entonces, nosotros queremos estudiar algunos modelos que puedan dar cuenta de esto. Principalmente modelos como, por ejemplo, acople preventivo de tercera generación. El acople preventivo de tercera generación soltado, por esto queremos centrarnos en posibles anomalías, diseños que vamos a encontrar con un tau en el estado. Nuestra fábrica de tau va a ser un DHC, ¿sí? Con el protocolo que en estados que al final resulten en dos taus. En general, los experimentos como Atlas, CMS y estos necesitan estudios de factibilidad para decir este modelo lo puedo observar, este modelo no lo puedo observar. Mirar qué relación de parámetros es observable, qué diferencias pueden haber, qué observables pueden ser interesantes, y este tipo de cosas las solemos hacer. Entonces, yo quiero dejar un examen de cosas que podemos llegar a tener cuidado. Por ejemplo, si quiero tener señales con dos taus en el estado final, pueden venir de muchísimas fuentes. Puede venir, por ejemplo, de un vector Z', de un Higgs pesado, de un Lepton-QUARK, y estas pueden ser tanto, el Lepton-QUARK puede ser tanto escalar. Entonces, si queremos diferenciar los modelos de álgebra de los modelos de trabajo, sencillamente podemos ver que cuando esto es un channel, debemos esperar una resonancia. ¿Sí? Como estos son t-channel, debemos esperar a. Entonces sabemos diferenciar entre este modelo y este modelo si vemos un posible excepción. Pero ¿cómo podemos diferenciar izquierda a derecha? Si queremos diferenciar de izquierda a derecha, tenemos que tener cuidado con exactamente la polarización del estado. Y además, podemos tener modelos donde de todas estas señales están conjuntas. Entonces, tenemos que ser capaces de diferenciar una y diferenciar la otra que estamos viendo. Y esto es en esencia el objetivo del proyecto que estamos tratando de desarrollar. Entonces, quiero para hacer ese efecto de interferencia. Entonces, como nos comentaba José, podemos, en el modelo estándar, por ejemplo, ya tenemos efectos de interferencia. Sencillamente que normalmente nos pasamos por algo. Podrías, por ejemplo, preguntar cómo producir dos estados a través de un Z y uno más tarde. La amplitud pues dependerá de la amplitud de gamma, la amplitud de Z, y este término de acá, que es un efecto mixto de ambos, es lo que vamos a llamar interferencia. Podemos ver cómo nuestra amplitud es plana para el mismo tono. Podemos ver cómo aparece nuestra resonancia para el Z. Fíjense, por favor, que depende de la energía de ese de masa S y que cerca a la masa al cuadrado de la masa de Z, entonces podemos tener un pico en esta distribución de acá. Sin embargo, el término de resonancia es un poco complicado. El término de resonancia para este caso particular no tiene este cuadrado. Y al no tener este cuadrado, entonces podemos S es más pequeño que la masa de Z, la interferencia o esta contribución va a ser negativa. Entonces decimos que tenemos una interferencia destructiva. Si S es mayor a la masa de M, entonces decimos que tenemos una interferencia constructiva. Fíjense, por favor, que depende de S en el numerador. ¿Eso qué implica? Esto implica que apenas vamos a ver unos pequeños efectos de interferencia alrededor de la masa del Z. Pero esto no va a ser necesariamente el caso. Cuando S es pequeño, pues esta distribución sería que no hay problemas a baja energía. Entonces, miren qué pasa en los modelos. Este modelo estudiado en años anteriores, publicamos este paper a finales del año pasado y miramos un poquito estos efectos de interferencia en un modelo bien específico que voy a llamar el modelo parecido de Boson. Entonces, ¿cómo lo tenemos? Como diciendo, una posible solución a los problemas de diferencialidad electrónica es introducir un lector en esta teoría. El lector es sencillamente una partícula hipotética que tiene un vértice combinado un quark y un lepton a través de alguna partícula. Esta partícula, pues precisamente es un lector quark. Entonces, nosotros queremos construir un modelo. Quiero asumir, por ejemplo, que el medidor puede ser vectorial, por decirlo. Entonces, construyo mis corrientes vectoriales, miro qué características, qué números cuánticos debería tener mi lepton quark, y me doy cuenta, por ejemplo, que tiene que ser simplemente de SU2, que tiene que estar atacado color y que tiene que tener hipercarga. Construyo mi derivado. A partir del derivado, tengo cuál es la interacción magnética que puede tener este lepton quark. Y pues puedo agregar unos matrices de acople que me distinguen entre generaciones. ¿Listo? Tengo cuidado con nuestros constraints experimentales. Y entonces digo, vale, tiene que ser preferente a la tercera generación si queremos que esté permitido. Y además, si quiero que solucione, por ejemplo, Therapy Star, entonces tengo que tener cuidado con este acoplamiento. Listo, pero en general va a ser despreciable comparado con los demás. Entonces digo, vale, que es el estado. Entonces hago un estudio de factibilidad, qué tan fácil es este modelo. Entonces, para modelar la energía general, implementamos en Python, pasamos por el sistema más de factibilidad de Higgs. Tomamos el estado final. Este estado final, hacemos algún análisis de datos. Parecido, podemos construir un discriminador y obtener un valor de significancia para mirar en qué regiones de parámetros nuestro modelo es observado. Entonces, un ejemplo de eso es, por ejemplo, el uso de nuestros estados. Esta variable estimate es parecida a la que se trabajan en modelos con Jensen. Entonces, nuestro estimate sencillamente nos va a decir, mira, van a tender a salir muy justos estos estados que tú estás proponiendo. Entonces, vale, me aprovecho de eso ver la cross-section para los diferentes niveles de acople y digo, vale, mi modelo es observable en esta región. Y esta región de acá es la que me soluciona, por ejemplo, bien anomalies. Entonces hay un pequeño chance, ya lejos, de que podamos explicar bien anomalies con este modelo. Pero, entonces ahí viene de gran pedo, es como, bueno, ese es el modelo que tú propones, que lo puedes observar con un. Pero tienen que tener cuidado para no sé si voy a proponer una palabra. Por ejemplo, si mi leptofar tiene un origination, debería haber llegado hasta la simetría. Entonces yo digo, vale, con la corriente, la masajeo un poco para acomodar y mirar cómo sería mi generador. Y yo digo, vale, pues si este generador está permitido, deberían estar permitidos lo que cierre el altera de. Si yo cierro la antena, que mi modelo predice también, no sé cuánto debe ser. Entonces dicen, vale, ellos bajo un tiro. Los generadores tienen que tener su definición. Tengo un switch, no tan este jornal bueno, una vez dicho, debería tener una tipo 1, pero sencillamente es visita prima. Construyo visita prima, y la mañana más general de visita prima, mi régimen de acoples, sí, o significa que carga las direcciones y estudio casos juntos. El problema está en que como este modelo, como el modelo permite ambas son direcciones, entonces tengo que tener cuidado con los términos de interferencia. Esto es un Dischargen, entonces esta es nuestra contribución, esto es un Dischargen, esta es nuestra contribución, y este sería nuestro término de interferencia. Cosas a tener cuidado que tenemos varios, tenemos un Dischargen, pero ya no vamos a proporcionar a eso. Entonces, vamos a tener problemas en energías de ferromagnéticas. Entonces, me puse a mirar cómo es la proceso diferencial de la producción del modelo que tiene nuestro leptofar. Nuestro está prima con cada una por aparte, es proporcional al término que le mostré y proporcional a los acoples. Piensen, por favor, que la resonancia se ve reforzada si la masa de nuestras partículas es pequeña. Y tenemos acá un poco de interferencia destructiva, pero al comienzo pues, no nos preocupamos mucho acerca de ella. Pero para altas masas, ese efecto ya es bastante considerable. Entonces ya no hay tanta refuerzo en la resonancia y tenemos un montón de interferencia destructiva. Eso hace que cuando yo vaya a mirar mi cross-section diferencial, la que está en azul corresponde a el caso de que los modelos están separados. Y a medida que yo los agrego, veo un incremento a bajas masas, pero veo una interferencia destructiva a altas masas a la hora de observar mi modelo, y eso pues tiene un impacto en nuestra sensibilidad. Por favor, pongámonos en las líneas púrpuras, que son las que les mostré hace un momento. Tenemos una región potencialmente observable de Decays, y cuando extiendo mi modelo a tener Z', entonces a bajas masas tenemos una región explorable que no teníamos antes. Podemos observar anomalías, podemos explicar anomalías, pero a su vez podemos perder a altas masas. Les diría, antes podemos explicar anomalías a otro nivel. ¿Listo? Y esa es esencialmente lo que les quería contar de Captcha. Saber que sencillamente no es proponer una nueva partícula, sino estudio sensibilidad mínimo efectivo, porque en función de una u otra condición, ustedes pueden ver cómo sus regímenes de sensibilidad van a cambiar drásticamente en función de tengo una interferencia. Esto te marca un proyecto más grande, tratamos de diferenciar diferentes modelos, mirar los posibles efectos de interferencia en la polarización de esos diferentes modelos. Entonces, por eso tenemos a nuestro colaborador Jorge, trabajando en nuestra pequeña composición de la polarización. Yo voy como estudiar esta parte de la interferencia. Y mirar cómo estas posibles huellas nos permiten estudiar un parámetro, explicar nuestras violaciones a nivel cerebral. Gracias.
Pregunta por aquí. Diego.
Una pregunta, esto es simplemente haciendo referencia a la conversación.
A ver, ¿qué puse acá? Sí.
¿Han considerado procesos científicos?
Sí, sí, sí. En este trabajo se hicieron distinciones a cómo se debería iluminar y proyecciones a alta velocidad, otros escenarios, porque aquí les decimos únicamente si el lector va a tocar repentes tirales derechas, que pasan escenarios mixtos, pues todos podemos estudiar, pero pues, como lo tenemos.
Pues, ¿cómo te reflejas el análisis en el trabajo que presentó anteriormente?
Bien, la intención, la intención es diferenciar. Nuestra principal intención es diferenciar este tipo de modelos dado posible que todos se en una condena. Obviamente acciones matan efectos de bus, acciones van porque sí, es como un primer. Entonces, nuevamente, si tú quieres diferenciar de arriba hacia abajo, te miras la distribución en la baja que subir. Pero si quieres diferenciar de izquierda a derecha, tienes que diferenciar en el estilo. ¿Sí? Entonces, lo primero que queremos hacer es, pues, aprendamos a ver el espectro. El experimento claramente lo sabe hacer, claramente no lee el espectro, claramente no puede reconocer los resultados. Entonces, nuestro primer trabajo fue, vale, queremos entender cómo este tema de la correlación del Z. Sabemos que fue medido para el Z, justamente para corroborar ese efecto que estamos buscando y el ángulo de mezcla está bien medido. Entonces dijimos que no.
¿Cuál es el mes?
Le vuelvo. La correlación es confusa. ¿Por qué? Entonces, dijimos, vale, usamos ese escenario, queremos reproducir los resultados, queremos mirar cómo se mira a nivel de integrador, a nivel de masa, cómo se mira a nivel de media, cómo se mira a nivel de edad, eso sería un problema a nivel de edad de integridad. ¿Sí? Seguramente ya hay un problema en la simulación que lo solucionar. Y pues, solución. Gracias a la sesión. Dábamos un exceso de grandes de caos, ya separan sus escaladas, si es resonante, tenemos que hacer un bien. ¿Y cómo podría eso deformarse por culpa de la diferencia? Ese es un momento. Gracias.
Casi me mato. ¿Más preguntas? ¿No? Bueno, agradecemos a Cristian. Bueno, que se vayan, que tengo dos anuncios que me pidió Eduardo. Uno es mañana es aquí, de vuelta a la mañana, y el otro es Ciencia al Bar, por favor. Ahora en un ratito José se va para allá y vamos a tener ese evento en la 15:37. Por favor, para que todos participen. ¿Sí? Gracias. Gracias por quedarse en la sesión. Gracias.
A ti.